I'm Jason McIntosh with McIntosh Applied Engineering. I'm going to show you how to do a measurement with the Surface Impedance Measurement Apparatus, also known as SIMA. This is the case that you receive. Inside, there's going to be a sheet of paper showing the original contents of the case. There's also a sound card driver, and then the actual measurement hardware. This is the SIMA controller. It contains the data acquisition hardware for the measurement process. It requires a power supply and a USB connection to your computer. There are also two measurement devices inside of the case. The larger one is the MAE 130. It has a 1-inch measurement area. The black disc is the area over which the surface impedance is measured. There's also the MAE 131. It has a 12 millimeter diameter measurement area for measuring acoustical impedance, and this is the one we're going to use today. It has a larger frequency range than the larger 130, but the 130 is better for lower frequency measurements. ARES consists of a series of modules for doing modeling and measurements. We're going to create an instance of the surface impedance measurement module. When you run it, first thing you're going to want to do is to select the Setup tab and make sure you've got the correct device selected. In this case, we're using the 131. You're also going to want to make sure that the controller has been found. And finally, enter an appropriate temperature for the air that you're working in, the room temperature. Next, we'll go to the Acquisition tab. There are two acquisitions that can be performed. One is a device calibration, and the other is the actual impedance measurement. Next, we're going to perform a measurement. So I'm going to pull the measurement type down and select impedance measurement. What I've selected to measure today is the volume. Let's go back over to the measurement area. The volume of just a simple 10-ounce glass jar. It's actually a jelly jar, and we're going to measure the impedance into this and get an idea of what the cavity modes look like in terms of the impedance this presents. So I want to put the 131 on this glass jar, but I need something to help me interface this better. So what I have is an aluminum plate 4 millimeters thick with a 15 millimeter diameter hole. So I'm going to putty this onto the jar, and I'm going to putty this SIMA onto the aluminum plate. So I'm going to go ahead and put the SIMA against the plate to kind of visually center the black measurement area in the middle of my 15 millimeter hole in the plate. Make sure it's down there good. And now I'm going to grab some more putty. I'm going to roll this out. And ring the lip of the jar with the putty. Put the aluminum plate over top of the jar, press down firmly. So now I've sealed the SIMA device to the jar through this plate. I'm going to go ahead and do the measurement on that. Back over on ARES. I'm going to specify the diameter of the area that we're measuring as 42 millimeters. I've already measured that. That's about the opening of the glass jar. I've set the frequency range to be as wide as possible, 20 hertz to 10 kilohertz. I've got log spacing off. The modes will generate a lot of high frequency detail, and log frequency is good for enhancing the low frequency detail, so I'm going to leave that off. And I'm going to change the data set name here to be 10-ounce glass jar. And I'll hit perform measurement. You should hear the SWIP sign run. May have to run a couple times again. And when it completes, it'll show the impedance in this graph here. Okay, Aries has finished with the measurement. We'll hit done, and we see all of the large impedance spikes due to the interior cavity modes of that glass jar. The glass walls are very stiff, and so these cavity modes have very high Q on them. And if we zoom in at the low frequencies, we see, try that again. We zoom in at low frequencies, we see the 1 over j omega effect with the imaginary part of the impedance indicating that we have a sealed volume. You can actually use this to compute the volume of the air in the jar if you'd like. So now we've got a measurement of the jar without any damping in it. I'm going to add damping and show its effect on these cavity modes. So let's go back over to the measurement area. Take the aluminum plate off. And I have a piece of felt here, just a regular piece of felt, kind of chopped up a little bit. I want to put that in the glass jar, so it's, maybe about 20% filled with that felt material. That's going to act to dampen the acoustical modes, cavity modes of that jar. And I'm going to put the putty back on. And let's go back to Aries. Now I'm going to change the dataset name, and I'm going to add with damping material onto the dataset name and repeat the measurement. It's taking a couple sweeps to get the measurement. And now we see the impedance into the jar with the damping material present. We still see the effect of cavity modes, but they're much more damped than previously seen. And at low frequencies again, let me zoom in here, look at the behavior under 500 Hertz. We see the j omega effect. So we haven't changed the low frequency volume impedance effect at all, but we have dampened those modes out considerably. I'm going to go over to plotting tab. I'm going to select both of these for plotting, and you can tell that the impedance with the damping is much less than without the damping. Those volume cavity modes present a tremendous impedance spike at those modes, whereas with the damping material, even a little bit of damping smooths them out considerably. Now I'd like to show what you can do with this impedance in mating it up with the modeler. So I'm going to export these impedance curves to some files. So I'm going to go to the Files Clipboard tab, select Save, and I'm just going to save them into this directory. Select the next one, save, and I'll hit save. So both of them have been exported to my directory. Now I'm going to go up and create a modeler module. In this modeler module, I'm going to make a simple speaker, radiating speaker model. But I'm going to, for the rear of the speaker, I'm going to use the impedances that we just measured. Rather than creating a volume element here in the Aries modeler, I'm going to import that impedance data into this resistance, acoustical resistance. and I need to put a pressure release on the other side. I also need to put a radiation element in front of the speaker. And I'm just going to use the default parameters for the speaker and the radiation element. They're not going to be optimized by any means, but there'll be something to see what the effects are. And finally, I need a graph to view what's going to happen. I'm going to go to this resistance element now, and I'm going to, for the impedance, instead of using the static acoustic ohm impedance that you'd enter in, I'm going to load in the impedance with the glass jar. And then I need to check this to tell it to use it. And I'll hit calculate. Let me find that graph. So this is the graph that was created with the solution we just ran. And we can see the effects of those modes a little bit, but our frequency resolution here is pretty poor. So let's go back. We'll select the global tab, global parameters tab. And instead of doing 200 frequency points, let's do 2000. Hit calculate. Go back to the graph. And now we see the effects of those resonance much more clearly. So it's having a large effect on the output of this speaker, a very undesirable effect. We're putting these big resonance in there, and that's probably going to cause some weird sounds and possibly some buzzing going on. So we definitely don't want this for the rear volume of a speaker. So let's go now and load in the impedance curved with the damping material, that felt in it. Before I run the model, I actually want to copy the undamped case out into buffer A, and I'll plot it. And now I'll hit calculate, and I've got buffer A with the undamped in the green curve, and the damped is in blue. To make that a little more visible, I'm going to go to the graph controls, and I'm going to increase the weight of these lines a little bit. Let's set them to a weight of 3, which is going to be pretty heavy. Should be able to see it better. So here we've got the curve with in green again is with the undamped. We see these large spikes in the response of the speaker. And with the damping, let's zoom in. The pressure response from that speaker is much nicer, much more well behaved. So this is an example of how you can use the SIMA device to measure the impedance of a volume, and then you can import that data into Aries modeler and use it to predict what the effects would be if that impedance was used as the rear volume of a speaker. But that's really just the beginning of what you can do with SIMA and Aries. You can measure the impedance of ports, of materials, of horns, measure the impedance into your ear, and you can import that impedance into the modeler to either use it directly in the modeler or see how your material impedance compares to the impedance that you're actually using in the model, and then better correlate your model to your measured results. Or you can just use the impedance itself to show you, provide you with some information about how your acoustical system is behaving. So I find the application of it to be just wide open, and I hope this has been a good introduction for you. And if you have any questions about the capabilities, you're welcome to contact May at any time. You can email us at support@maellc.com, and we'll be happy to answer any of your questions. Thank you.